Okay, I was just notified that we are live. We're on YouTube and we're on the recording. Before I introduce the speaker today, I want to take a moment to thank Mike Simonovich for the semesters long work that he's done in all the setup, all the advertising, all the notices, all the YouTube streams that he's put together. I wouldn't have known how to do 2/3 of these things. Mike is a master at it. He just, in fact, showed his mastery in just a nice minute or so, getting things going in unexpected difficulties. So thank you, Mike. We really appreciate your efforts for the semester. Okay, now we have today a PhD student, Guoqian Yan, who's working with Dr. Matthews. You see her people on her committee. Guoqian has 2 degrees, bachelor's and master's from Northeastern China Normal University before she came to the University of Florida. And like many of Dr. Matthews' students, she's studying spatial patterns and rainfall of environmental moisture associated with hurricanes in the North Atlantic Basin. So, Guoqian, why don't you just go take it away and tell us what you have to say.
Thank you, Dr. Binford. Good afternoon, everyone. Welcome to my colloquium presentation. Sorry about the issue with my camera, but luckily you can still see my screen, so that's good, so we can begin. So my presentation is about the variation in the spatial pattern of the rainfall and environmental moisture associated with hurricanes in the North Atlantic Basin. My advisor is Dr. Matches, like Dr. Binford has already introduced, and my committee members are Dr. Mosa, Dr. Feek, and Dr. Gerben. A little bit overview about the tropical cyclone. So a cyclone refers to a closed rotation of air blowing in a circular pattern and spinning in a counterclockwise direction in the northern hemisphere. Tropical cyclone specifically mean the cyclone that develops over the warm ocean water in the tropic latitudes. It is characterized by the low atmospheric pressure, high winds, and heavy rain. Once the tropical cyclone reaches wind of at least 63 kilometers per hour, they are typically called a tropical storm and assigned a name. If the maximum sustained wind reach 119 kilometers per hour, then the tropical cyclone is called a hurricane in the North Atlantic Ocean. Below the figure, we can see the global tropical cyclone formation basin. And for my study, I mainly examine the hurricanes in the North Atlantic Basin. So anyway, it didn't work. Yeah, mainly in this green area. So that includes the North Atlantic Ocean, the Gulf of Mexico, and also the Caribbean Sea. TCs are one of the most devastating natural hazards to the society due to numerous fatalities and enormous economic losses. Approximate 2,544 deaths happened from TCs in the US or its coastal waters between 1963 to 2012. Regarding the economic losses, the average annual normalized damages from TC in the continental US is around $4.8 billion in the 71-year period from 1925 to 1995. TCs can pose devastating threats to society and environment through 3 major aspects: storm surge, the upper photo, the heavy precipitation, middle one, and the intense wind at the bottom picture. Among all the hazards associated with TCs, precipitation related to the TC as well as induced flood can lead to significant economic losses and fatalities over broad regions adjacent to and away from the TC track. So for my first paper, I studied the rainfall from 2 data sets, MSWEP and the TRMM and compare them with the rain gauge and stage 4 radar for hurricanes in the North Atlantic Basin. For these two data sets, I will have a detailed description later. A little bit in introduction. So during the 1962 and 2012, nearly 50% of the TCs with fatalities had at least one death from the freshwater flooding in the US. 1 inch increase in rainfall can increase total fatality by 28%. Therefore, understanding the landfalling TC-induced rainfall is critical in forecasting the impacts of rainfall and issuing the flood warnings. Furthermore, if we want to examine how rainfall evolves during TC's whole life cycle to better forecast the rainfall after landfall, only detection of the TC rainfall over land is not enough. So we need a data set that can detect the TC rainfall both over land and over ocean in order to capture the rainfall change of the whole TC's life cycle. As we know, ground truth often comes from the rain gauge data. However, the rain gauges are irregular distributed, so they are not dense enough to detect some local changes. In addition, no rain gauge data is available for the ocean. Ground-based weather radar from the National Weather Service provides better continuous spatial coverage and also better spatial resolution. However, it only covers 230 kilometers around each station. Thus, the rainfall estimates from the satellites provide a valuable alternative data source in analyzing the rainfall characteristics of the tropical cyclones. I will mainly talk about two satellite estimates. One is the Tropical Rainfall Measuring Mission, TRMM. It is one of the most commonly utilized data sets for the analysis of the rain rates over both the ocean and land. It is a 3-hourly data available in 0.25 degree spatial resolution, covering 50 degrees north to 50 degrees south from 1998 to present. Since a lot of researchers have used this data to conduct the TC rainfall analysis, so we have known that TRMM has several disadvantages. It tends to underestimate the high rainfall and overestimates the light rainfall. Another data set, the multi-source weighted ensemble precipitation, MSWEP. It is a pretty new data set. It optimally takes advantage of a wide range of gauge satellites and reanalysis data to supply reliable precipitation estimates with high temporal and spatial resolution globally. Compared with TRMM, MSWEP is a truly global data set with 0.01 degree spatial resolution. Furthermore, MSWEP provides a continuous precipitation record for around 40 years, at almost 2 times long compared with TRMM. An important difference regarding the data set is that TRMM provides only an instant rain rate at some point within the 3-hour window rather than the 3-hour total. However, the MSWEP provides a 3-hour accumulation, which is more accurate. Because for the TRMM, if we want to obtain the 3-hour total, we must multiply the TRMM data by 3, then it can introduce a bias when the high rain rate are overrepresented and the low rain rate or regions of no rain rate at the time of the snapshot are also overrepresented in the 3-hour total. Two comprehensive large-scale evaluation about the MSWEP has been performed, and it is proven that MSWEP performs best overall. However, little evaluation relevant to the TC rainfall in the North Atlantic Basin has been conducted using MSWEP yet. So my research questions are: first, between MSWEP and the TRMM, which graded precipitation dataset produces values closer to the estimation from the rain gauge and stage 4 radar in terms of the daily total precipitation for hurricanes in the North Atlantic Basin? Second, how do MSWEP and the TRMM perform in light, moderate, and high rainfall compared with rain gauge and stage 4 radar for hurricanes in the North Atlantic Basin? Third, how much variation exists in the spatial pattern of hurricane relative rainfall areas from the MSWEP and the TRMM over ocean and over land for hurricanes' whole life cycle in the North Atlantic Basin? The data, what I use hurricane data and also the precipitation data. So I choose 10 hurricanes making landfall at the US and lasting for at least 2 days after landfall in this study. Since we know a majority of hurricanes, they couldn't last more than 2 days after landfall. The track of the hurricanes are obtained from the International Best Track Archive for Climate Steward (IBTRACS) dataset. This dataset provides 3 hourly TC center positions 8 times each day for Atlantic Basin since 1951. Rainfall data pertaining to HTC are obtained from 4 sources: the MSWEP, the TRMM, the Global Historical Climate Network Daily Rain Gauge Dataset, and also the Stage 4 radar. The method I use is mainly ship metrics and the statistic method. So first, the 3 hourly graded rainfall data are obtained from MSWEP and the TRMM. For the TRMM, we multiplied the original 1 hour data by 3 to get the 3 hour total. After that, the 3 hourly MSWEP and TRMM, the 6 hourly stage 4 radar are summed to covering a 24-hour period to get the daily rainfall total. Then we extract the daily precipitation value from the MSWEP, TRMM, and stage 4 radar based on the rain gauge location corresponding to the day within 500 kilometers of the daily hurricane track. The 500 kilometer is a very useful and important distance, since a lot of researchers agree that the rainfall happening 500 kilometers within the TC should belong to the TC. After we got the rainfall from the 4 datasets, then we compare the daily rainfall amount from the MSWEP and the TRMM with rain gauge and the radar respectively by calculating the roaming square error. Roaming square error is a frequently used measure of the differences between the values predicted and also the real value. Here, we treat the rain gauge value and also the radar value as the real value, and the MSWEP and the TRMM as the observed value. We use the relative roaming square just to try to consider the rainfall amount influences. Because we will use the roaming square and divide by the average rainfall, then it will give us kind of like a unit roaming square error, which is more meaningful and accurate. Then the mean when you test a non-parametric test is used to test whether the relative roaming square error are significantly different between the 2 data sets. And I choose the threshold 0.05 as the significant level. Similarly, this is also for the rainfall comparison, but we divide the rainfall into 3 categories. The light rainfall with the rain rate value of 3 millimeters per 3 hour, and moderate rainfall with the value of 7.5 millimeters per 3 hour, then the high rainfall with the value of 50 millimeters per 3 hour. And we also repeat the previous 2 steps to calculate the relative room square error and then conduct the MSWEP test. For the shape matrix, first, we obtain the rainfield polygon from the MSWEP and TRMM, also based on the previous defined light, moderate, and heavy rain rate threshold. Then we get the area for each polygon. As I mentioned, the 500 kilometer is very important. So only polygons whose centroid are located within 500 kilometer of the storm center and with a minimum of 5 pixels are selected for the further analysis. When we get the rain field from the MSWEP and the TRMM, then we calculate the shape matrix, circularity, and dispersion and fragmentation. Use these equations. Here is an illustration about the meaning of these 3 shape matrix. So basically, circular means it is whether it is round and dispersed, and the fragmentation is a critical measurement for the compactness of the TC. After we get these shape matrix indexes, we use the Wilcoxon side rank test, which is also non-parametric test to compare the distribution in the paired samples. For the result, so for the total rainfall comparison with the rain gauge and the radar, based on the result, we can reject the new hypothesis. So it means relative room square error between the MSWEP and the rain gauge is significantly different from that between the TRMM and the rain gauge. And also similarly, the same conclusion for the radar. So from the box plot, we can clearly see that the median value of the relative room square error between the MSWEP and the radar is much lower than that between the TRMM and the radar, and also a similar situation for the rain gauge as well. So which means MSWEP produce values more close to both the rain gauge and the radar. Then we look at the rainfall at the different threshold based on the previously defined light, moderate, and the high rainfall value. And we did the same process. Also, the results are significant. So from the box plot, we can see the relative room square error between MSWEP between MSWEP and the rain gauge are much smaller than those between the TRMM and the rain gauge for all the 3 categories. Similarly, we got the identical conclusion when compared with the radar as well. So based on these 2 analyses, we can see that MSWEP produce the rainfall value more close to the rain gauge and the radar for the 3 different rainfall category: light, moderate, and high, which means the MSWEP has the potential to overcome the disadvantage of the TRMM, since we have known that TRMM usually overestimate the light rainfall and underestimate the heavy rainfall. After that, we calculate the Wilcoxon, we calculate the shape matrix indexes, and also we use the Wilcoxon rank test to compare them based on the 3 different thresholds, and also before landfall and after landfall. From the result, we can see that before landfall, MSWEP and the TRMM are all significantly different at 0.05 level. After landfall, the higher rain rates are more similar in general. We can see like the moderate and also the high rainfall category. MSWEP and the TRMM datasets have different rain fields before versus after landfall, except for the 15 millimeters per 3 hour threshold. The rain fields are always larger in the MSWEP. TRMM is always more fragmented than the MSWEP, and it is also more dispersed, except for the 15 millimeters per 3 hour category after landfall. For the MSWEP, it is always more circular, except for the 7.5 and the 15 millimeters per 3 hour after landfall. The rain fields are less circular, more fragmented, and dispersed after landfall in both datasets, which totally makes sense. So based on this, we can get an idea when we try to use the data to analyze the flooding area. Things we have proven that the MSWEP value is more close to the rain gauge and the radar for the daily total, and also for the 3 different thresholds. So since compared with the rainfall area, the MSWEP has some significantly different with the TRMM, so we can consider this when we study the flooding area. That's my first paper, and my second paper is the spatial and temporal evolution of the environmental moisture associated with hurricane in the North Atlantic Basin. One important thermodynamic factor influencing the TC formation and maintenance is the availability of a large amount of environmental moisture, which is the vital component for the TC's water budget. Characteristic of the TC's precipitation depends not only on the nature of the storm, but also on the available moisture. Large-scale moisture is a primary controlling factor for the TC size and also the outer rain band activity. From the previous study, we have known that the TCs, they could obtain environmental moisture from the radiance as far as 4 times that of their wind circulation, as illustrated in figure 10. From the figure 10, we can see usually we see the 500 kilometer is the radiance of the TC. Then it means the TC can get the moisture from as far as the 2,000 kilometer from its center. Total precipitable water, TPW, I will use this variable later, but here I just first mention it. So for the TPW, it is an indicator for the moisture availability. It means the depth of the water that would accumulate if all moisture in a column extending throughout the troposphere condensed and fell as precipitation. From a global perspective, the regions where the TCs form usually have total precipitable water TPW values greater than 40 millimeters on average. So for my research questions, first, over the North Atlantic Basin for the tropical cyclone achieving hurricane intensity and making landfall over the US, how does the moisture associated with them vary spatially? Second, how does the moisture associated with TC vary when they are originated from different regions? Third, how does the moisture associated with TC vary when they are within 48 hours of US landfall force. How does the moisture associated with TC vary when they first intensify from tropical storm to the hurricane? For the data I used in this analysis, I chose 30 hurricanes from 1998 to 2017 making landfall over the United States. Like I mentioned before, the average, the total precipitable water, TPW, is from the Statistical Hurricane Intensity Prediction Scheme dataset. For the 5 different annulus regions from the TC Center. From the figure 11, the left one, we can clearly see what does it mean. So it means the TPW from the 0 to 200. So that's the core in the center, and 200 to 400. So that's the second annulus area, and 400 to 600 and 600 to 800, and the most outside one is 800 to 1,000 kilometers. So I used the averaged TPW for this 5 annulus region. And the tracks are also from the IB tracks. I mainly use 2 methods for this analysis. First is the hotspot analysis. The hotspot analysis identifies statistically significant spatial cluster of high values, which are the hotspots, and the low values, which are the cold spots. It employs the GTS or GI star statistic. This statistic measures the intensity of the clustering of the high or low values in a point feature relative to its neighboring point feature in the entire data set. It can generate z-score, which is a standard deviation, and also the p-value, which is the statistical probability. In the next slide, I will have a figure showing these 2 values. So it generates the z-score and also the p-value for each point feature, which can indicate whether the moisture associated with a given point feature is statistically clustered compared to the moisture in a neighboring point feature, as well as the moisture across the entire analysis domain. So the larger the z-score suggests that there is more intense clustering of the value. Second, I also use the mean when you test. It is applied to examine whether the environmental moisture associated with the hurricane are significantly different between the different subgroups. The non-hypothesis is that there is no significant difference between each 2 compared groups. This non-hypothesis will be rejected if the p-value of the test is less than 0.05. These are the results for the hotspot analysis. From this figure, we can clearly see that obviously there are mainly 2 colors in the figure. So the red one represents the hotspots, and also the blue one represents the cold spots. The darker the red, it means the higher confidence level, and the darker, also the darker the the blue color, the higher confidence level. So these 4 from the top left is the TPW from 0 to 200 kilometers, and the top right is 200 for 400, and the bottom left is 400 to 600, and the bottom right is 600 to 800. And when we look at them together, we can see that majorly the hotspots are located in the Gulf of Mexico and the Caribbean Sea area. And from the 0 to 200, and going out from the TC center, we can see the hotspot extended more south and more west. More east. And for the cold spot, they are majorly located along the US coast. Based on this is a spatial pattern, so we decide to subdivide the data into several subgroups. So first, we divide the whole sample based on their origin locations. So from the figure 13, we can see 13 hurricanes originated from the North Atlantic Ocean area in yellow, and 17 hurricanes originated from the Gulf of Mexico and the Caribbean Sea. They are in green. And through the MSWEP test to examine their moisture for their whole life cycle, the non-hypotheses are rejected since the p-value of the MSWEP test are all less than 0.05. So we can know that the TPW are significantly different for all the 5 different annulus regions in the 2 subgroups, A and G and C. So from the table 5, we can see the median moisture for hurricanes originated from the North Atlantic Ocean are lower than those for hurricanes originated from the Gulf of Mexico and the Caribbean Sea. Next, we divide the whole sample based on their landfall location. For the figure 14, we can see that we divide them into 2 regions. One region is the east coast of the United States, and the other region is the Gulf Coast of the United States. Through the MSWEP test, we also rejected the non-hypothesis. So the TPW are significantly different for all the 5 annulus regions in these 2 groups, E and G. And also, we can see that the median moisture for hurricanes landfalling at the Gulf of Mexico of the United States are higher than those for hurricanes landfalling at the east coast of the United States. Then we look at the 2 subgroups individually. First, let's look at the group of hurricanes making landfall at the east coast of the United States. We test the moisture 48 hours before the landfall, and also the moisture at the time of the landfall using the MSWEP test. Based on the result, also the original non-hypothesis are rejected. So the TPW are significantly for all the 5 different annulus regions at 48 hours before landfall, and also at the landfall time in the group E. And we can see the actually the 48 hours before landfall median moisture is higher than that for the time at landfall. From the box plot, we can see from the 48 hours before landfall and until the time at the time of landfall, every 6 hourly data, we can see in general, it has a decreasing trend. However, we should notice that this decreased trend is not linear, especially for the 0 to 200 kilometer region, and also the 200 to 400 annulus region, which means there are some cases that can experience the moisture increase during this process. But finally, when it making landfall, the moisture decreases finally. I look at the cases and I noticed that some of them have that situation because they experience another intensification before landfall. So that can advect the moisture from the outside region. So the moisture for the inner core area, 0 to 200, and also the kind of like eye wall area, 200 to 400 region can have the higher moisture. Another subgroup G, which means the hurricanes making landfall at the Gulf of Mexico. Similarly, the result is similar as the previous group. So also we rejected the non-hypothesis, and the moisture just decrease 48 hours before landfall. But we can see also for the 0 to 200 and 200 to 400 region, the moisture is not linearly decreasing. So the last analysis is about the results for the total precipitable water comparison during the intensification phase for the from the tropical storm to the hurricane. In order to unify the data, so I just analyzed the first intensification, since some of the cases they have experienced several intensification. For the quickly intensifying and slowly intensifying comparison, first I divide them into two groups based on their median value. However, the result is not significant. So I just use the less than 25% time as the intensifying cases, and more than 75% time as the slowly intensifying cases, and using the Mann-Weinberg test to analyze the moisture. From the table 9, we can see that for the annulus, for the region 0 to 200 kilometer and annulus region 200 to 400 kilometer, the result is not significant, which means actually for this region during this process, the moisture is not significantly changed. And for the outer region from the 400 to 1,000 kilometer, the moisture is significantly different. But interestingly, we can see that for the quickly intensifying cases, the median value is smaller than the slowing intensifying cases, which does not match the previous literature. And the reason may be due to the time lag effect of the moisture. Since we look at the time that from the tropical cyclone to the hurricane, however, we should look kind of like the moisture advanced to the certain time in this process, kind of like the moisture in the previous time will influence the TC intensification. So another explanation for this may be because it's quickly intensifying, so it advects the moisture from the surrounding area into the TC center. Thus, the surrounding area has the less moisture. But I need to do more tests to get a robust conclusion about this. And also for the comparison between the tropical storm phase and the hurricane phase, I just compared these two specific time, how the moisture change. And for these 2 times, only the 0 to 200 kilometer area. So that's the inner core area of the TC. The moisture are significantly different. For the other regions, there's no significant difference. Also, there may be a lag effect associated with this. So I plan to explore more later. So for the conclusion, compared with stream, MSWEP produces precipitation values closer to the estimates from the rain gauge and stage 4 radar in terms of the daily total, light, moderate, and high rainfall for hurricanes in the North Atlantic Basin. MSWEP and the TRMM datasets have different rain fields before versus after landfall, except for the high 15 millimeters per 3 hour threshold. The rain fields are always larger in MSWEP. TRMM is always more fragmented than MSWEP, and it is also more dispersed, except for the high threshold after landfall. MSWEP is always more circular, except for the moderate 7.5 millimeters per 3 hour and the high thresholds after landfall. The moisture hotspots are mainly located in the Gulf of Mexico and the Caribbean Sea, while the moisture cold spots are mainly along the along the coast of the United States. Moisture are significantly different for hurricanes with different origin location and landfall locations. Moistures can be declined 48 hours before landfall. However, the decreasing process is not always linear. There could be time lag effects for moisture associated with TC intensification process. For my future work, I plan to include more TC cases and examine more rainfall datasets for the TC rainfall. And I plan to utilize the graded moisture datasets to better detect the spatial distribution of the moisture in 4 quadrants around the TC center. Also, I would like to consider the time lag effects of the moisture further out at the TC for the intensifying process. So that's all. Thank you.
Okay, Guoqian, you can't hear the applause, but everybody's applauding.
Thank you so much.
There is 3:45. We have at least 5 minutes for questions and more time than that because those of us who can stick around till 4. So I'm just going to throw the door open for questions, the floor open for questions, and let people blurt them out. Jump in, please.
Okay, Mike, everybody's being very polite as usual, so I'm going to jump in and be totally rude. Thank you very much for a really interesting talk. Obviously well prepared. I thought that your hypotheses and your tests were all laid out really nicely.
Thank you.
What I was wondering is in the final analysis there, were you prepared to be a little bit or go a little bit farther and say what you think might be going on? So, why do you think that the hurricanes that come ashore on the East Coast have different characteristics to those coming ashore along the Gulf of Mexico? Is there something about the way the circulation pattern goes, where they're drawing their moisture from, what the temperature, what percentage of the time those winds spend over warmer water? Then, I've listened to Corey enough and to learn a little bit about sucking in dry air off of the continent and how that might affect them and affect their shape. So I thought that, it was wonderful. You've done a tremendous amount of work and you've been very thorough in your testing. I sense Dr. Fick, jumping all over you perhaps on some of those things. But I just wondered if you feel a little bit of confidence to throw out some physical hypotheses about what might be going on and why these observations you might be finding on the basis of this very rigorous piece of work.
Thank you, Dr. Whalen. I mean, your comment and the question are very valuable. Definitely, yeah, I think you are also a professional professor in the meteorology area. So definitely, like you mentioned, first for the TC formation, there are several, requirements. As we know, the sea surface temperature should be like, certain degree, and also like the low level disturbance should exist, and also there are some other influence definitely. So that's the reason why, I mean, for this analysis, I didn't kind of like refuse to think about the other mechanism. Definitely I want to, however, due to the limitation of this data set, so it is just an averaged moisture for us annulus region. So it is hard to detect some, detailed information. Like you mentioned, if we want to do that, we need to include more data sets and consider more situation, like the wind shear, and also, if possible, the sea surface temperature, and also the other stuff. For this analysis, it's kind of like the observational study to show how the moisture associated with this TC and how they changed, kind of like, based on 30 cases, what we can get. Definitely, it is worth exploring what you mentioned, but I'm sorry, due to the limitation of this data set, I cannot do that analysis with this data set. I hope I answered your question, but yeah, feel free to ask more if you think I didn't answer all your question. Yeah.
Well, I think that you've done a wonderful job. Don't get me wrong. You've got these significant differences, interesting geographic significant differences, these that you've drawn from these data, and I wonder if you could put it back in the context of other people's work about, why there are these spatial variations.
Gotcha. Yeah, definitely. I think that's a good aspect I should work on. Yeah, kind of like try to connect that to other factors and to better explain the mechanism behind this. Definitely, that's a good aspect. Yeah.
And then I'm only saying that because I think, particularly if this is some sort of a practice or preparation for a job talk, perhaps, but you've got to pull people like myself and other professors who are not hurricane experts. You got to pull us back to your original questions and what contribution that you've made to it. So we know that you're rigorous, and yes, you probably lost me, several of us going through this, but at the end, I'm going to trust that you've done the analysis correctly. Now I want you just to tell me, and this relates to those major points I had at the beginning about losses, millions of dollars of losses, about the number of people who died and so forth. So you say, oh yeah, right. So here was someone studying a really valid, important question. They obviously knew what they were doing. They got a good grasp of the literature. They've got the right data. They've done the analysis. And now they're going to just fold this back in and say about at the beginning. And so really, I'm thinking more for an audience of geographers or perhaps other people, other earth scientists who are not tropical cyclone experts. Tell us why what you did was important and how it fits, but you don't have to answer that right now. But that's really justifying me jumping in with both feet.
Thank you so much.
In a nutshell, Guoqian, what does it mean, and what does it mean to the rest of the world? So no, I agree with you, Pete. That was the one place. Everything else is wonderful. Anybody else? It is 3:51, so if you need to go, please feel free to. If not, we'll stick around for a few more minutes and Guoqian can answer other questions. Well, I will say something. I'm going to ask a question. I had my comment in. This is the last meeting, the final meeting of the colloquium for the fall semester in the geography department. We will not have a meeting next week at the end of the classes. So faculty, please send your evaluations to me. I sent you a copy of the form beforehand. We need to populate the student learning outcomes, even though, as I said, we should be learning from the students at this point. And students taking the class for credit, please upload your evaluations to the Canvas site so I can keep track of who was here and make sure that you reflected a little bit on what was said and understand the vast diversity we find in geography departments. So with that.
Dr. Bedford, this is Jason. Can I chime in for a moment?
Yes, please.
Great. First, thanks, Guoqian. That was a very interesting talk. I just want a reminder from the graduate coordinator side of things. If you are a graduate student participating this semester, not for credit, and you need a letter from Dr. Binford stating your participation in the class so you can receive credit later, please do that with Dr. Binford before finals week is over so we can get that paperwork filed, because it does have a tendency to come in late, or we have a tendency to not be able to find it, and that just creates some confusion later. So if you need credit at a later semester, please make sure you get that letter from Dr. Binford in the next week or two. Thanks,
Jason,
Mike.
would you like for me to send you copies of all those letters, or do you want to wait for the student to do that?
Actually, Mike, I'd be just as happy to get it from the coordinator. So that'd be great. If you can send them over, that'd be good. And I'll note, each time that they've been filed.
Right.
Great. Thanks, everyone.
Okay, we still have time. People are still logged on. 23 of you are still listening. You must have questions for Guoqian.
Okay, so this is Jason again. I will ask one, Guoqian, that I was curious about. And that was, can we look at your GEDIS statistic where you looked at the different distances?
Distance. So you mean the 48 hours before landfall?
Yeah, slide 24, I think it is.
24. That's hotspot.
Yeah.
Okay.
Right. And that was performed with a GEDIS statistic, right? Yeah. So you
yes.
You set 4 different distances. So at least in GEDIS's original arguments, they suggested that there's some kind of a critical distance, right? That maybe one of those 4 distances is more important than the other. Did you do any kind of analysis to ensure that when your GI bin size increased, that your GEDIS statistic increased at the same time your probability remained significant?
Sorry, I didn't do that.
So do you think that would have an effect on the sort of the hotspot membership? And if so, do you think that would affect your overall results and what went on to be your next analysis?
Okay, thank you, Dr. Blackburn. That's a good aspect I didn't think of before. I can try to do that, but actually, I didn't count any of the, how to say, I mean, I didn't, I just look at the spatial distribution and the pattern, but I didn't mean to count the number of the hotspot and the cold spot, numerically. So I can try to do that and to see whether that will change my spatial pattern for this. Yeah, but sorry, I didn't do that before. I'm not sure whether that will change, but yeah, since I mean, like the mechanism of the algorithm, it has compared with the surrounding location and also the whole data set. From my point of view, it shouldn't change that much, but I can definitely try and to see whether it will change or not.
Yeah, so GEDIS and ORD argued very explicitly that if your GI values aren't increasing with distance, then that it's not only probability, right, but they have to go up, because the assumption is that the farther you look, the more likely you are to falsely assign events into a cluster. It's what they call like a spillover, right? So you just, as you get bigger, you just start pulling more members into your cluster.
Okay.
So I think it would just be interesting to think about, or at least have a limitation that, you know, that you didn't test for that.
Okay, got you. Thank you so much.
Okay, anybody else? Going once, still 14 people on, going twice. Okay, Mike Simonovich, once again, thank you very much for the entire semester and for the work that you did today. I think we can close her down now and go on and be prepared for the next spring, for next